Okay, welcome. Here's a quick recap of the kinetic friction on inclined plane lab that we did today. I'm going to go quickly through the data, some sample data, and help you hopefully with your analysis. I have provided in Teacheries a link to this sample data. However, it looked to me when you guys left that everybody had a good enough data set to do their own analysis. So this would be an example of how you would do the analysis. If you really can't use your own numbers for some reason, you could go ahead and substitute this sample information. I'm going to start with the second of the two graphs because it's a little bit easier to understand. And in this case, they ask you to graph the friction force with respect to the normal force. Now, to refresh your memory, we got this friction force from a fairly complicated equation. It had to do with taking the pull force and subtracting the component of weight in each case. So that was your more complicated equation, but it's your simpler result. And the reason it's simpler is because we have in the past graphed friction force with respect to normal force, so we should be familiar with this relationship. In this case, it should make sense as the normal force increases. In other words, as the two surfaces are pressed more firmly together, the friction force increases, and as that normal force decreases, the friction decreases. It decreases in a very specific way. You can kind of see here that we have this one point right here, which was the point we put in manually, that when we got to vertical and there was no normal force, we found that the friction force was 0 because the pull would just have been the weight of the object. So that gives us a very, very special point here in this relationship. If we wanted to model this relationship right here, we could come to the Analyze and Model feature, something like this. Looks like I got to choose this other. There we go. Make that the active graph. Come down to Model. That looks better. And you can kind of see here that our correct choice. It is the graph of a line, but it's specifically the graph of a line that goes through 0 intercept, and that means it's proportional. So in this case right here, I can call this proportional. And let me just go ahead and make this a little bit bigger for you to see. There we go. And in this case, I'll go ahead and just use the keyboard to make some adjustments here. You can kind of see I'm a little too high here, so I can kind of bring it down into the range, something like this. I could be a little more subtle with this, maybe 0.3. That looks a little bit better. This is something that you'll have to do yourself. Now, in this case right here, what we're using this graph for is to notice that friction force is proportional to this normal force, and because it's proportional, this constant of proportionality here, this value for A, the thing that is multiplied by the normal force to give us the proportional friction force, has an actual meaning in physics. And you'll have to think about that and provide that for your lab analysis. That's all I'll say for right here. Now, the reason I said that this was the simpler analysis, not just because we had done it before, but because this idea of the friction force being proportional to the normal force, when we did it before in the lab, what we did was we added, on a flat surface, you added more and more weight. In other words, increasing the normal force and then checking out the friction. In this lab, really, we just did the same thing. Instead of increasing the weight by adding more stuff on, we increased the incline, which changed the normal force. So it was just a different, more complicated way to do the same lab that we did before. But what we did not do before was something associated with the data that you had in your first graph, and that looks a little something like this. This is, again, from our sample data. This is the graph of the force, the mean force. In other words, this was essentially the pull force. For the average pull for each of the events, as opposed to the angle for each of the events. And you can kind of see here the scale associated with the angle. Now, the idea behind this graph is a little more complicated than the other graph because it's certainly not a linear relationship. You can kind of see here it's some kind of a curved relationship. We said because of the analysis that we did before with the free body diagram, we know that this curve right here is likely to have a very special relationship. And this is the pull force associated with the angle. Now, to help you with that, what I'd like to do is actually produce one new graph for you to look at real quick. So in this case, I'd just like to program up using the model feature in Logger Pro a graph of the weight down the plane with respect to an angle. And what we said was this. We said that if we go to Analyze and Model, we said that the component of weight down the plane is mg sine theta. So in this case right here, what I'm going to do is I'm going to choose the sine function. And I'm going to go ahead and just set some numbers here to 0. So I'm going to set this c term to 0. We don't need that, and we don't need this term right there. And you can kind of see here that I have what would be considered a normal sine function, a sine wave. And I'm going to go ahead and accept that. Okay, so let me put this off to the side here so we can kind of see this shape. Now, when you think of weight down the plane, we never got a graph that looked like this. This is the graph, but that's the graph of a sine wave. If you've ever seen pictures of, obviously in math, you've done a full sine wave. So the question is why are we even using the sine function associated with our data? Well, what you'll notice is this sine function right here is for one full cycle. And a full cycle is, if I read down here, 360 degrees. But of course, what we're doing with our incline is only rotating at 90 degrees. So if I go ahead and change this value over here, I'll change it to 100 so we have a little edge, we can see the edge. So I'm going to change my scale now to 100. Now you can see, again, I need to move this out of the way, you can see the shape of the portion of a sine function that fits the data that we're interested in. And this is what the weight down the plane looks like as a function of the angle of incline. In other words, when the board is flat, there's no weight down the plane. There's no tendency for it to slide down the plane. When I am at 90 degrees up here, I have whatever my weight is of my object, something like this. And you can kind of see, not linear, but there's this sort of a relationship where you pick up quite a bit of weight down the plane in the first, let's say, 60 degrees, but then it flattens out and it's not that much of a factor in the last 30 degrees of your pull, okay? Or changing the incline. So this is the key. This is the first graph that you need to understand. This is the straight graph of how the component of weight down the plane for a frictionless object looks like as the incline is increased. Now, the question is, what does this graph look like when you add friction into the mix? And now this should make sense now. I'll go ahead and change this to 100 as well. There we go. And now you can kind of see a very similar shape. Now, it is a similar shape, but is not exactly the same shape as we saw before. You should notice a difference here that should make sense. In other words, the force of the pull on the cart, even when this is at 0 incline, no angle of incline, right, still has some sort of a force associated with it. That should make sense when we add friction into the mix. And then of interest here is the basic shape associated with the actual graph of the data. Now I'm going to take this one step further now. Now this was not required in the lab, but I do want you to see that we can create with Logger Pro and in physics in general more complicated models than we have used before. Okay, here we go. Now we said that this pull force from our free body diagram, when we add friction in, is the previous graph. In other words, that portion of the sine wave, mg sine theta, but it also includes the component associated with friction, which, if you remember from our equations, was mu times the normal force, and the normal force is mg cosine theta. So we can use all of that information to create a much more complicated model that looks a little something like this. Now I've put this in advance, but this is showing that ramp friction. There's your weight, mg sine x is our angle, so weight down the plane, plus the friction component should be what our pull is. And once again, I'm going to have to change my graphs here. Sorry about that. Let me try this again. Click on the graph. There we go. Now it should load on to the correct graph. That looks a little better. And I'm just going to go ahead and accept that and make this so you can see it a little bit better. There we go. Okay. So not a particularly good fit of the data, but of course we haven't adjusted our numbers here. You should have gotten the number, I'm not going to say how you got it, but your analysis should have given you a number for your value for mu. Weight is something you found in your lab. In this case, I'm going to give the weight that they used for their sample data. Looks a little something like this, and ba-bing, there we go. So in this case, what this is showing is that not only in log or pro, but also in physics in general, we can handle much more complicated mathematical models, but still create relationships that reflect what's happening in reality. This is the real situation of dragging an object up an incline. This is the real shape that you get from your data. This is a nice confirmation not only of our theory that we had between the relationship of friction and the normal force, but also the relationship, the trig relationships that we have used for inclined planes. It shows that this stuff actually works. So hopefully you enjoyed the lab. I do give you credit. This is the most abstract and the most complicated of the labs we've done so far, but you guys did great. Just do your analysis. Do the added problem, which is an AP problem on inclined planes, and that homework is due on Tuesday night at midnight. Good luck with your work.